All right. Aloha and welcome to Monday. Nice of more of you to show up this day and week. We are going to be continuing on from last week. Just as a review of what we did last week, we learned how to be able to take a H plus concentration and convert it into hydroxide concentration. We know we can take a H plus concentration and turn it into a pH. We also learned last week about a concept called POH, which is just taking the OH minus concentration. So if we're given the OH minus, we can find something called the POH. And we learned that their pH and POH are related by a pretty easy relationship of 14 minus the other one to get that. So if you have this table, you can get between all of these different things. In lab this week, this table will be of the utmost importance for you to be able to do the things that we're going to do. So we also talked about pKa being with all the different Ka values that we had. We could look at the strengths of different acids, right? Remember that we said that the acids, where are the acids? It was a long chapel. No wonder it took so long to. So we have all these different acids, right? We said that they have all these different values, and the larger the Ka, the stronger the acid. But we said that we don't like working with numbers like 5 times 10 to the negative 7, 6 times 10 to the negative 3, 8 times 10 to the negative 12. So what we learned was what they do in chemistry is they take all of those Ka values, and just like they do a pH, which is a negative log of H plus, or a POH, which is the negative log of OH, that means that a Ka is simply the negative log of the Ka values. And that basically told us that when something has a larger Ka, that means it has a lower pKa. So the stronger the acid, the smaller the pKa. And then we also said that there's this thing called Kb that we're eventually going to learn about. It's the same thing as Ka. Ka is representing an acid after it deprotonates to make H plus and its conjugate base. Kb was studying a base. Well, so it's a base plus water making BH plus OH minus. So these are all aqueous. And this was a liquid, so we eliminate the water. So it's BH plus times OH minus over the concentration of the base originally. So we're going to do some calculations with all of this stuff in a bit, but there's also things called PKBs, which helps us measure base strength and stuff like that. So at this point in the semester, everything we've been doing, and we're just doing it a little bit higher level. If you didn't learn it good the first time for a lot of this stuff, you're going to have to learn it. So strap in and get ready to learn some stuff. So let's talk about the things that we're going to actually have to do. We're going to lab this week. We're going to have to calculate the, what was the name of the lab again? Who said it? Determining the Ka and the Kb from the actual pHs of the solution. So what we're going to do in lab is we're going to find the pH of a solution. Anybody have any ideas how we're going to do that? pH meter. Stick a little probe in something, it's going to give us a pH. From the pH, can we calculate the H plus concentration? Yes, we can. We learned that last week. From the H plus concentration, we can plug that into an ICE table, and using the concepts we learned in ICE tables, like if we know what the initial concentration was and we know what the equilibrium concentration is, we know what X was, we can solve that for everything, and then we can basically solve for Ka. So let's go ahead and look at some problems like this, okay? Now, with acids and bases, we have to determine if it's a strong acid or a strong base, or a weak acid or a weak base. How do we tell if something is a strong acid, Jack? So it's just a list of strong acids that I gave you, and that list is located over here. Where is it? Strong acids. So these are the strong acids. If it's not a strong acid, what does that mean, Bailey? Then it's a weak acid. Do you have to memorize all 100 weak acids in the world? What do you have to do, Ella? Very good. So if you wanted to know who's the bad, like you don't have to know every good person in this class. You only have to know the four bad people. I'm just kidding. But basically, if you know like the strongs and it's not a strong, then it is by definition going to be a weak acid. For anything we deal with in this class, there probably are some other exotic strong acids that we'll never see in this class. You'll probably never see in your life unless you go into like hardcore chemistry, in which case you'll learn all those exceptions to the rule. Okay, so let's go into calculating the pH of a acid solution. So let's start with acids. If we are talking about a strong acid, what's the definition of a strong acid? Ian, what's a strong acid? Remember? It does have a lower pKa. It has a super high Ka. In fact, it's so high. How high is it, Bryce? What's a strong acid? It is a strong electrolyte, but what is like the thing about a strong acid? Good. So if we have a strong acid, right? If we want to find the pH of a strong acid, so let's take one step back, right? The Ka of an acid. What is an acid? This is going to be the acid equilibrium dissociation constant. So if we have an acid HA and it's a strong acid, Lucian, what does it become? There is an A. What else? So it separates into H plus and A minus. Okay? This is aqueous. This is aqueous. This is aqueous. If we're doing a Ka, what do we do for Kas? We take all of the aqueous things, the products we put on top, the reactants we put on the bottom. So the products are the H plus and the A minus, and the bottom is HA when it's intact. So strong acids all dissociate into H plus and A minus. So let's say that if we were all acids and us being an acid was all of us wearing a hat, okay? Everybody with me on this analogy? So if we all have hats on and the hats that we're wearing are protons or H's, if we were all strong acids, when we came in the room, we would all take off our hats, okay? Because we would all be dissociated from our acidic proton. Does that make sense? So if we're a strong acid, every single one of us comes in. We're like going to church in the South and you don't wear, I don't know. I don't go to church anymore, but you know, and I don't talk about church in class until then, but do we all see, we would all take off our hats, right? If we were weak acids, we'd have people like, I'm not taking off my hat for you. So we walk in the class, the ones who are respectful take off their hats. I usually wear a hat, so I don't really think hats are disrespectful. Don't feel like those of you wearing hats now, I hate you. Just kidding. But if we were all weak acids, maybe 10% of us take off our hats. The other 90% keep their hat on. Okay. So that's basically the difference between a strong acid and a weak acid. The strong acids, every single acid takes off its proton. They all separate. So if we're trying to calculate the pH of a strong acid, if it's a strong acid and we have 1 molar of HCl, if we want to calculate the pH of 1 molar HCl, because it's a strong acid, do we all agree that we would have 1 molar H plus and 1 molar Cl minus? Because every single one of these strong acids took off their hats or their protons, right? Everyone agree with that? So when you're calculating the pH of a strong acid, you don't have to set up an ice table or anything like that. You just have to know the concentration of that strong acid, and that is how many H pluses it has if it is a monoprotic acid. What do you think monoprotic acid means? Anybody have a thought on that? What do you think that means, Robert? So what's mono? And what does protic probably mean? Could mean one proton. So HCl can only give off one proton, so it's a monoprotic acid. What I'm saying is, of that strong acid list, all of these are strong acids except for this one here that says diprotic. So H2SO4 is going to be a very special case. We're not going to like use this same theory for the strong acids for this one because it actually gives off two protons. So we're going to like take a special look at sulfuric acid on its own. But every other one of these acids, if I gave you 0.1 molar perchloric acid and I wanted you to tell me what the pH of that solution is going to be, how do you think you would do this, Alondra? Can you tell how much H plus is in solution of a 0.1 molar HClO4 solution? What do you think? How much? Very good. We would have 0.1 molar H plus and 0.1 molar ClO4 minus. Now, to find the pH of this solution, the pH of the solution is equal to the negative log of the H plus concentration. Everybody see that? So how would I calculate the pH of this solution? What would I do, Abby? I need to take the negative log of the H plus concentration. Do I know the H plus concentration of this 0.1 molar HClO4? 0.1. So you would just type into your calculator negative log of 0.1. Anybody got that for me? The 1? It would be a pH equal to 1. Okay? So finding the pH of a strong acid is super easy for the most part. Everybody agree with that? Same thing is going to happen with bases, okay? Remember that we have some strong bases. Strong bases dissociate. If we say that these strong bases dissociate, if we have a 0.5 molar KOH solution, could we find the pH of this solution? What do you think? Kaylee? What does the fact that it's a strong base mean? What did it mean to be a strong acid? It meant it completely dissociated, right? So what do we think a strong base means? It's also going to completely dissociate. So if we have 0.5 molar KOH, that is going to dissociate into 0.5 molar K plus and 0.5 molar OH minus. Everybody see that? So if I want to calculate the pH of this 0.5 molar KOH solution, I have to realize it's a strong base. That means all of this base is going to be dissociated. Can I find the pH directly from the OH minus concentration? What do we think? This is where we have to use that little table that I had here. This table right here. So if I know the OH minus concentration, it's 0.5 molar OH minus, but I want to find the pH, I have to either convert OH minus into H plus using this formula, or I find the POH doing the negative log of 0.5. What is the negative log of 0.5? That would be a 0.3 would be the POH of this solution. Now, if I do so because it was a strong base, that's why I know exactly how much OH minus was in solution, right? I find the POH of that OH minus solution, and then how can I get to the pH? Valerie, what can I do? Very good. So since I want to find POH, 14 minus POH, which is 0.3 right here, 14 minus 0.3 would tell us that we have a pH of this 0.5 molar solution equal to 13.7. Does it make sense that a strong base solution would have a pH of 13.7? Yes, Natalie? Why? So on the pH scale, above 7 is a basic solution, and a strong base should be a pretty high number closer to the 14. Could we go the other way? We could have done OH minus concentration. So we want to go this way, actually. I'm sorry. The H plus concentration, we could have done 1 times 10 to the negative 14th divided by 0.5. Anybody do that for me? So once again, if you're not using your calculator right now, you're going to be in for a rude awakening on this third exam. What did we get? 2 times 10 to the negative 14th. And that would give us H plus. And now we can use pH equals negative log. So do negative log of 2 times 10 to the negative 14th. 13.7. So do we see that if we take this road to get here, we get 13.7, or if we take this road to get here, we get 13.7. It's really a matter of what do you like to do better, right? I mean, if you get dropped off at the front entrance of campus, do you have to walk straight down this path and over here? Or can you walk past the bookstore and still get here? Can you still get here by walking different pathways? Yes, you can. Your friend likes to go this way. You like to go this way. Do you have to go that way? No. You do whatever makes you more comfortable, and that's the way it's going to be, okay? So basically, we've learned how to calculate the pH of strong acids and strong bases, okay? All this stuff that this is talking about is like slowly, methodically, annoyingly talking about all the different things that are negligible or not really. So when we are looking at like the pH of a strong acid or a strong base, technically, we look at how much OH is produced or H plus is produced from that strong acid or base. And technically, there's a little bit of OH or H plus produced from water dissociating. But if something makes a crap load of H plus and water makes a couple, 1/1,000,000th the amount, do you have to add that 1/1,000,000th? Will that affect the pH? No, it will not, okay? So in these cases, that's what all these slides are. For all those of you who are systematically looking at these notes beforehand, take a second to laugh, everyone, okay? Because I'm pretty sure no one is looking at the notes. Did you all know that all of the notes that I give you in class are available beforehand, free of charge? You don't even need to pay me anything for all this work that I've done in the past getting it, copying out of a textbook. But if you feel like I meant to today, put all of your scores. So I graded the exams through the Scantron. I stapled them. I circled everything wrong. So I do plan on having your exam back by Wednesday. Okay. Between classes, I was gonna put in your raw scores before I put in the partial credit, just to give you all a little jolt of like, oh crap, that was not as good as I hoped. And then when you get it back, you're like, oh, luckily he gives partial credit. Okay. My wife's like, you're crazy to do that. I'm like, I know, but I care for the students. But, I'm slowly faltering in that. Okay. So the third exam, I am not going to give any partial credit. Okay. And that's for real. A lot of stuff I say is made up, but that is for real. And you know the reason why I'm doing that? I plan the third exam to be a take-home exam. So you're going to have a lot of time. No one is going to have any issues with time. Are you celebrating that hard that I just said that? Oh my gosh. So the third exam, I'm going to let you like have maybe like 5 days. It is an individual exam. So if you cheat, whatever's the worst punishment you can think of, that's not going to happen. But, don't cheat, okay? So I just wanted to make it so I was never here for an exam until the final, okay? So I plan on giving the last exam as a take-home. But you know what happens when you have a take-home exam? Is it usually easier? Probably not, okay? Do not use the internet on it, okay? When you put in some random thing from the internet, I'm gonna know. When you use Chat GPT to try and do my problems, I'm gonna put something specifically wrong. So we'll see, okay? One time I gave a quiz when this class was all through COVID. One day you were in that one? Were you in the class? No, it was not horrible, okay? So I gave a quiz. I accidentally put the wrong answer. So then people who like took the quiz early got it wrong, and then they told their friends. So then everybody like cheated, and you got the wrong answer. So I knew they were cheating because there was no way to get that answer unless you straight cheated. So I caught half the class cheating. And my wife was like, "You can't do that." I'm like, "I've already got 10 people telling me they cheated." So
You actually got it right and graded wrong. So
yeah. Yeah, and I went back and corrected it. So maybe I will do that for this exam, okay? So you're gonna get one chance to submit it. Don't go ask your friend, like, "Oh, you've already done it. What's the answer for two?" I mean, it's probably gonna be right, but just be aware that sometimes if you cheat, you might get caught, okay? So don't cheat. Just learn the material and do it good. You have time. You're going to have, I mean, I would still approach this class like taking notes and things because a lot of the stuff from this test will be on like cumulative to the final. Most of the stuff we've learned is not going to be like, so I'm not really going to put anything from chapter 13 on the final, okay? So if you didn't learn chapter 13 good, when you get this back, you should make correction, but realize that stuff sucks. Okay. That was a crappy chapter. So I will not force you to learn that your whole life. If you become a kineticist, I'm sorry, but you will learn it at a high level when you get there. Okay. Now let's get back to doing these problems. So for basically for the different monoprotic strong acids, whatever the concentration is, you take the negative log of it to find the pH. Now, for bases, it's the same. But if we have like a 0.1 molar calcium hydroxide in bases only, if you have 0.1 molar calcium hydroxide, Jessica, what is the actual concentration of hydroxide? Is it 0.1 because it's a strong base? What is it? Close, but the opposite, right? So if you have 0.1 molar of this, CaOH2, and then we separate it out, we're going to have 0.1 molar Ca2 plus, but because there's two OHs for every one of the full, we'll have 0.1 molar of one OH minus plus 0.1 molar of the other OH minus. So because this is, I want to say diprotic, but it's not diprotic, hydroxylic. I don't know. There's not really a good word for that. But notice how when you have 0.1 molar of this strong acid that has a stoichiometry of two OHs to one CaOH2, does everybody see that you would actually have 0.2 molar of OH minus, right? There's twice as much OH minus. So now let's think of it like this, okay? If we're all coming into class and we're wearing mittens, and if mittens are the hydroxides, each person takes off all their mittens because they're a strong base. If there's 10 of us in here, how many mittens get taken off? Twice as much, right? So since one calcium hydroxide has two OHs for every one CaOH2, if it's 0.1 molar CaOH2, there is twice as many mittens. Does that make sense? So when something's mono, it makes one. So we use like hats as an analogy. When it's something that has 2 to 1, it's going to be like this, okay? So that's something to consider when doing strong acids and strong bases, okay? So strong acids and strong bases are going to be easy. What's going to be crappy is going to be the pH of a weak acid. Explain to me why it's crappy, Ida. Why do you think it's going to be harder to do the weak acid? What's the definition? You don't know? What do you think, Nana? What is the definition of a weak acid? So think about the definition of a strong acid. What was it? And use the word fully and dissociates in your definition. It fully dissociates. Very good. So it fully dissociates. So what, therefore, must a weak acid be, Ricardo? It doesn't fully dissociate, right? So if we have a 0.1 molar, let's say HF, that's one of the like stereotypical weak acids, what that means is we will not have 0.1 molar H plus, and we will not have 0.1 molar F minus. In fact, it's going to be some percentage less than 0.1, okay? Do you think we'd be able to figure out what that percentage is, Bianca? How do you think we could figure it out? To do what? Say it again. Yes, we're going to use the equilibrium constants. So all that equilibrium stuff we learned, remember ice tables and stuff like that? Guess what? That is back. I said chapter 13 wasn't going to carry on. Chapter 14 will carry on strong. Okay. So if it doesn't fully dissociate, it means it dissociates partially. So what that means is you will have some questionable amount of H plus, some questionable amount of F minus, and at equilibrium, this will be minus X, this will be plus X and plus X. Remember all of this stuff? Ice tables? That's how we're going to learn how to do this, okay? So look at this real fast. Everybody understand how to do it? Can we move on? Yeah? We'll go quickly through each step, okay? So let's go through each step individually. You didn't get that, Ella? I thought you looked at the notes beforehand. I thought we made a deal to look at the notes before class, not for me, for you. Dustin? So what is this first slide showing us? What is this thing called here? Very good. So this question is asking, find the H3O plus concentration of a 0.1 molar HCN solution. Everybody comfortable with that? So what I'm going to ask you to do is HCN is our weak acid. How do I know that this is a weak acid? Yeah, Emily? Because it's not a strong acid. Therefore, we know it's not going to be a full 0.1 molar H plus. So we know we start off with 0.1 molar. Why is there this little equal sign right here? And why not just 0? Any thoughts, Merve? Very good. There's always going to be a tiny bit amount of H plus, but guess what? It's usually going to be negligible. So that's what that whole negligible thing was saying. We're always going to assume that the amount of stuff in there originally is not that important, okay? There are times when it is important, but we're not going to waste our time learning the most complicated stuff in the world. So we can say it's about 0, and there's definitely no Cn minus dissociated before the reaction has time to come to equilibrium. So what do we know for sure about this, Loet? Which is the plus and which is the minus side? Which side do we put the plus on? Correct. Remember, anytime we have a 0 on one side, you can't go the other way. You can't lose from 0. So this is going to be plus, and this is going to be plus, and this is going to be minus. What variable do you think we should put in, Michelle? I mean, let's use X. Do we have to put in any 2X's or anything like that? Or is everything 1-to-1 ratio? Any thoughts? They're all 1-to-1, right? One of these makes one of these and one of these. So we're going to minus X from here, plus X, and plus X. Everybody comfortable with that? That tells us that at equilibrium, we have 0.1 minus X, 0 plus X, which is just X, and 0 plus X is just X. So do we have an equilibrium expression? This is called K, and since this is for an acid, we're going to call it Ka. Okay? Everyone comfortable with that? Now, what is going to be the equilibrium expression? H plus times Cn minus over HCN. Okay? This is just from using our products on the top and our reactants on the bottom, and we leave out the water because it's a liquid. Everyone remember this stuff? Yeah? Okay. So I'm going to put in these values. X, so let me color code this. This X is from the H3O plus. This X is from this one, and it's all divided by 0.1 minus X. And that equals Ka. Do you think there's a value of Ka somewhere? Do we have values of Ka anywhere for an acid like, let's see. So this table over here What acid are we dealing with in this? Was it HCN? Do we see HCN in this list? Hydrocyanic acid has a Ka equal to 4.9 times 10 to the negative 10th. Now, if we were doing this third exam in class, would you rather have the exam in class in 15 minutes? I'll let you think about that, okay? We'll take a vote on Friday. And that'll be easy since there'll only be like 15 people here. I don't have to like count too hard how many hands there are, okay? So if I give you an exam, it's up to you to have to like look up these Ka values and stuff. So basically, we can say this is the Ka of HCN. We can plug that into right here. So we get 4.9 times 10 to the negative 10th. What is something we can say about the value of this Ka right here? Any thoughts, honey? Is it large or small? So based on the fact that it's small, does everyone agree that we're not going to make that much products? That's the definition of a small Ka, right? So do you think we could say 0.1 minus x, and if x is going to be a super small number, can we assume that that x is negligible? What do you think? Sure. I mean, 0.1 is not the most concentrated, but if we're going to make like 0.000000001 molar that we lose, that is pretty negligible compared to the 0.1 we're initially starting with, right? And because this number is small, assumption should work well, right? So now we could then solve and we could say 4.9 times 10 to the negative 10 equals x squared over 0.1. We bring the 0.1 over. So let's go back to our slides. Okay. So I'm going to erase all this stuff. So we subtracted the x's, we added the x's, right? I showed you this. We find the equilibrium concentrations. We're then going to take our equilibrium value. We're making the x's small assumption. We plug in the Ka value. How did I get this Ka value right here, Riley? From the previous weak acid list. Very good. Okay. So you will have to look up that list over there. Okay. Like I said, it's all in the notes. I will not give you any acid. I mean, more likely on the exam, I will probably give you a generic acid called HA and I'll make up the Ka, because if I ask you to find the pH of a 0.1 molar HCN concentration, guess what you can do? You can type it into some AI bot and they'll figure it out, right? If you have the rich AI bot, then maybe you could even do it with my super secret fun thing. But, guess what? If you cheat, you're only going to cheat yourself in the end, okay? Later on, when you're on College Jeopardy and you have to find the PK, I'm just kidding. But you don't want to cheat, okay? You don't want to go down bad habits. So we solve for this. We take the square root of each side. Well, first we brought the 0.1 over. We did the square root of each side. We get 7 times 10 to the negative 6. What is this? 7 times 10 to the negative 6 divided by 0.1 times 100%. Gives us 0.007%. Is that less than the 5% rule? Hella. So it works really good. You could plug your answers back in. And now the K value, so whatever we got for K for X, the X value is 7 times 10 to the negative 6. And remember that X was equal to the H plus concentration. That was what we wanted to find. Oh, so we wanted to find the Ka of this. What? Oh, so this is plugging it back in to see if it works. So when we plug in the 7 times 10 to the negative 6, we get 4.9 times 10 to the negative 10. What was the value we had before? 4.9 times 10 to the negative 10. It is giving us the same value. We feel confident that that was a good job of doing that, right? So what this tells us is that X value the 7 times 10 to the negative 6 equals the H plus concentration. If we wanted to find the pH of this, we just take the negative log of this value and we find the H plus concentration. Everybody see how that works? So in lab, we're going to find the pKa of something, right? Or what was it? Nana, what was the lab again? Finding the pKa? Okay, so finding the Ka, right? So in lab, what you're going to do is we're still going to have this ICE table, right? Let's find it. So in lab, we are going to actually be able to solve for the H plus concentration right here, which means we can then work backwards and then solve for the Ka working backwards, okay? So maybe we'll talk about that on Wednesday, but I want to keep going. So this is showing how to do all of that. My suggestion to you, we're not going to do this together in class because I want to continue on with our work. Find the pH of a 0.2 molar HNO2 solution. Here is the stepwise way to do it. This is the answer you should get. Try this on your own after class and see if you get that, okay? We're not going to do that together. Here's another example where the approximation doesn't work, which is lame, but so let's see. When we look at this problem, we're doing 0.1 molar HClO2. Let's look at it, okay? So in this case, let's actually do this because this is what we're doing for lab. Determining so these are two different examples of doing the problems we just did. I would suggest you try it on your own. The only problem with using this one was the Ka of this was 0.0011. Is that a super small number? It's really not that small, right? So when you use the X is small approximation, this doesn't work. So you have to use the quadratic equation for this one, okay? So if you want to do that on your own, even though I'm giving you a take home, I probably won't give you the quadratic equation. I think that is just math and this is chemistry. I want you to learn how to do stuff, okay? Let's learn how to find the Ka from the pH of a solution. So let's say we have an unknown weak acid that we call HA. Excuse me. We know that is 0.1 molar. And what we do is we take a pH, we stick our pH probe in, and we get a pH of 4.25. Determine the Ka of this acid from the pH that we found. So this is pretty much exactly what we're doing in lab this week, okay? So what are we going to do? We have the pH is 4.25. Let's calculate the H plus concentration. So if pH equals negative log of H plus, but they give us the pH is 4.25 equals negative log of H plus. How do we find H plus concentration? We bring the negative over. So we times both sides by -1. So we get negative 4.25 equals log of H plus. And can we just divide both sides by log? What do we have to do, Robert? So we have to do 10 to the power of negative 4.25, 10 to the power of log H plus. This 10 to the log cancels. So it just tells us that H plus equals 10 to the negative 4.25. So let's go ahead and put that into our calculator and see if we get the right answer. Okay. What is 10 to the? That is just the way you get rid of logs, okay? Like I'm not going to teach you a math lesson on logarithms, but that is what you do to get rid of a log. Everybody comfortable with that? What did you get? Kiana, what'd you get? Anyone? Very good. 5.6 times 10 to the negative 5. Did anybody get something different? Everybody's perfect with their calculators. Wonderful. If you don't know how to do it, then talk to me after class. I have some time after class today. Okay, I'll help you with your calculator. Calculator skills is of the utmost important for these problems because it's a bunch of crappy math stuff that you can't do in your head, right? So basically now we know what the equilibrium concentration is of this. Can we figure out anything else from that? Remember, this was on the last exam. If we started at 0 and we ended at 5.6 times 10 to the negative 5, what does that mean, Angelina? How much did we have to add to 0 to get 5.6 times 10 to the negative 5? So we have to add 5.6 times 10 to the negative 5. That also means to the a minus, we add 5.6 times 10 to the negative 5. And that also means we subtracted 5.6 times 10 to the negative 5 from the initial concentration of our weak acid. Everybody see that? So now we know, and look at this. 0.1 minus 5.6 times 10 to the negative 5 in your calculator is going to give you like 0.9999999 something. It's basically the same as 0.1, right? And I wrote it wrong. 0.0999999, which is basically equal to 0.1. So now we have our equilibrium concentrations of each of these three things. The Ka, we're going to plug in. We're going to plug in. We're going to plug in. And now we can calculate the Ka of this weak acid. Everybody see that? Does this week's lab look super difficult? No. Awesome. I'm hoping we get out early this week. I'm hoping we get out early every week, to be honest, but sometimes we got to learn some stuff. So I believe this is a formal report. This will be a lot easier formal report than the last one, right? Where you had to do all that kinetics, graphs, and crap like that. You're going to have to do an ICE table. Think it's going to help you for the test? Probably. Okay. So, any questions on how we determine the Ka from the pH of the solution? Go tell your lab teacher, I taught you something before lab for once, okay? Hooray. So, any questions on this? We know how to do all this stuff? Anybody not know how to do it? I'm sure some of you don't know how to do it. In the real world, there's a saying, the squeaky wheel gets the grease or something like that. Anybody know what that means? What does that mean? Like, are you gonna go like it has to do with, I think, trains, right? And if there's a wheel squeaking, like if you have a door in your house that is squeaky, what do? Just don't go in that door anymore, right? Don't sneak into your parents' house in the squeaky door. You go in the back door. Well, what else could you do? You could grease that thing, right? But the other hinges are like, what the heck? Why don't you grease me? I'm working just fine. So the thing is saying, if you never ask for help, I'm not going to give you help. Okay. If you come and talk to me, I'll help you. Just so everyone knows, we got like four or five. I don't know. It's very little and I'm very happy. There's not that many weeks left in the semester. Okay. If you are having a hard time, I'm not just going to be like, oh, you did bad on this test. Let's talk. Most of you don't even come in and talk to me and I don't even know you. So if you need help, it's not too late to get help. Okay. Remember, this second exam, I still have to get partial credit, but there were some bomb scores and not bomb in the good way. I'm talking like if I put the scores in, I'm going to put the scores in today just to like give you all a little fresh of like, oh, damn. But remember, your lowest exam score will be substituted with your final exam score. So even if you got an F, you can get 100 on the final and still get an A in this class. So just kill the rest of the semester, okay? Is that the case in all classes? No, some classes you dig yourself a hole you can't get out of. You still have the time to boost yourself up in this class, but it's going to take some work, okay? So let's see. We understand how to, so if we look at this and we see it's 3.1 times 10 to the negative 8, we can then go, which of these acids would most likely be the unknown acid that we're working with? Any thoughts? Hydrofluoric. Where's hydrofluoric? Yeah. So probably this hypochlorous, which is 2.9 times 10 to the negative 8, right? This one was 3.1 times 10 to the negative 8. Are those the exact same answer? Does the stuff we do in lab always come out exactly perfect? Usually not, right? So if we're only off by 0.1, 0.00002, we feel pretty good about that for a lab setting, okay? So that would mean we used hypochlorous acid. Let's do a quick concept check. The initial concentration and Ks of several weak acids are listed. Which of these is the extra small approximation least likely to work in finding the pH of the solution? Okay, so which one so what do we want for the approximation to work? What are the two things, Abri? Jackson? Okay. So probably the one with the smallest Ka is probably the assumption will probably be fine. It also has a very large initial concentration, right? So think of it like this. How do I know? If you're gonna lose some money, right? If your K is really small, that means you have a really small tax that you have to pay. Some of you probably think of tax refunds. Sometimes when you get older, all you have to do is pay. It sucks. Okay. That's coming up in like 8 days. Damn. So if you had $1 million and you had to pay 5,000, it sucks, but it doesn't suck that bad, right? If you have $10,000 and you have to pay $5,000, that's going to cripple you, right? Now, if you have $1 million and you have to pay $5, obviously that doesn't matter. If you have 10,000 and you have to pay $5, it probably also doesn't have to matter, right? So that amount you have to pay is dependent on the Ka. A super tiny Ka means you're not going to take that much away. So the things with the smaller Kas are probably going to both be eliminated, right? So we can eliminate those two. Those approximations will probably work. Now, these have like semi-big approximation. Which one do you think it's going to hurt more? The thing with a pretty big starting or the thing with a very small starting? The small starting, that's the $10,000 person having to pay $5,000, right? So in this case, let's hope that the answer is C. The validity of the X's small approximation depends on both the value of the equilibrium constant and the initial concentration. The closer they are together, the less likely the approximation is to be valid. Okay? So you want your Ka to be very small and you want your initial concentration to be larger. And everything is relative. So if it's a question like this, look at your options and see which one makes the most sense. Okay? Now there's something called percent ionization. It's basically if you calculate the amount of H plus that is ionized over the initial concentration and you times it by 100%, then you know. So like if we're in this class, let's say we had 100 people exactly, right? If 50 of the 100 people ionize, we'd say 50 out of 100 is 0.5 times 100. We would get 50% of the class is ionized. If 10 out of the 100 ionize, it would be 10 divided by 100 times 100 would give us 10%, right? If 95% of us took off our hats, we would have 95% ionization, right? So percent ionization is just looking at the molarity of the H plus that you found dissociated divided by it's basically percent ionization is pretty much the 5% rule check. It's just you don't have to make it zero. I mean, you don't have to like if it's over 5%, that's fine. You just have to know what the percent ionization is, okay? I don't think I test on this that much. So let's see. That's all I have for you today. We will continue with this on Wednesday. Have a wonderful time. Come to class on Wednesday if you want your exam. I will allow corrections on this exam. You need to go to the tutor or the SI or myself to talk about them a little bit. You cool with that, Alejandra? People talking to you about that? You don't have to check anything. You just need to talk about it. I mean, I just wanted to come see you, okay? Yeah. I never check shit. I just make them look at it, okay? So come get your test on Wednesday. Unless I don't bring it. Aloha.